Okay, who's ready for some math? And also some memes. So I just want to go ahead and jump right in with a motivating example. So we have some Python code here. This is something that you could type into your interactive Python interpreter. To start off with, we have a simple function here where you take in two parameters, and we're going to randomly choose one of them to return. We're just using the existing random.choice function to actually do the work. The important point here is that I'm just trying to simplifying the parameter signature here a little bit. And if we invoke this function at runtime, right, we might get none, we might get 2, right? It really depends on the whims of the random number generator. If we call it again with different parameters, again, we don't know which of the particular arguments we're going to get back. We're going to get one or the other. Interestingly, though, we can now define another function called partial. This is also, in some ways, mimicking a function that exists in the standard library. You might know of functools.partial. This is a simplified version that is assuming that the function that you pass in, f, has 2 parameters. So you're going to pass in a function and one of the arguments. We're going to remember that argument. And then later on, you can invoke this partially applied function with the second argument. So here, for instance, we might call partial to remember that we were calling choose with none both times for its first parameter. And then we can invoke that partial function with the second parameter. We didn't have to repeat the first parameter that was remembered as part of the partial application. But again, we don't know whether we're going to get none or 2 back because we haven't changed the behavior of the function that we're calling. And then similarly, we can do the same thing with hello. And again, we don't know which of the results we're going to get back. Okay, so this is all just in the runtime interpreter. We haven't done anything with typing yet. But hopefully this example makes sense as we've sort of traced through what the different calls look like and what they return. So now, what would we do if we wanted to start type checking this example? So we can add some parameter annotations, some typing annotations here. Importantly, both of the functions are generic. We're using PEP 695 here to define the type variables that we want to use for these functions. We've added annotations to each of the parameters to show what we're expecting the types to be that come in, and then what value we're going to return as a result. Interestingly here, I've made sure to choose a single type variable for choose. You might think that there's other ways that we could type this function, but doing it with a single type variable is going to be important for the rest of what we look at. So we have some type annotations. What can we do next? So next, let's invoke multiplay, which is that going to be large enough? No, not even close. How is that? Better? Better? I'll have to scroll, but is that better? I can go bigger. Very good. More? Oh no! Now I have to go back this one. Okay, sorry. This will be the best I can do. I will describe what we see here too. Multiplay is a little tool that we vibe coded as part of developing TY, which lets us type in a snippet of Python code, and then it's going to run several type checkers against that same snippet of code. So we use this a lot as we're developing new features just to look at differentials between the different type checkers. And importantly, you can see that we did a reveal type just to sort of show what we get for each of those first calls to choose. And all of the type checkers are, well, there's a little bit of disagreement here. They're all showing a union of none with either literal 2 or with int. And so the details of like what's in the diagnostic messages are maybe less important, but you can see that all of the type checkers that multiplay checks are effectively producing the same answer. We were passing in none and 2. We have to unify that to a single type variable A, so we union the 2 types together, and that's what we get for the return types coming out the other side. Okay, now if we want to look at the partially applied example, right, so now we've extended the code to include the partial function that I had described on the previous slide. And here we are assigning to P, partially applying the none, and then we're trying to call it with 2 and with hello. And you'll see that basically all of the type checkers are reporting this as a type error. So even though this was at runtime something that we were able to do, all of the type checkers are reporting errors. And so now we're going to learn about why that is the case. So the first example was type checked correctly by all of the type checkers. The second example was type checked incorrectly, not by Microscope, actually. It did not produce an error here, but it does produce an any, but we can take that offline and talk about that separately. But otherwise, all of the type checkers are producing errors that are basically of the same form, which is that they're expecting you to pass in a value of type none, and 2 is not none, and hello is not none, and so you get a type error. Okay, so that's our running example. So let's start talking about constraint sets in TY. So I want to focus on constraint sets both as a way of exploring this example, of describing why that is the behavior that we're seeing from the type checkers, and maybe from that see if there are any possible potential extensions to the typing spec that would allow us to type check that correctly. Maybe we'll decide not to do that, as we'll see, but if we do, this gives us a language that lets us talk about what we would need to do in order to make that happen. So I'm Doug Creager, I'm from Astral. As of a couple of weeks ago, the acquisition did go through, so Astral is now an OpenAI joint, but I'm here to talk about constraint sets. So quick pop quiz. Let's start looking at some Python expressions, and I want to get from the audience answers to 2 questions. Is this expression that I've highlighted in yellow valid? And if so, what is its type? So real quick, this is a hopefully easy one to start with. Is this valid?
Yes.
Yes, it is. What's the type? Int. I say int. The type of the result of the call. Yeah. So I would say it's int. It's not literal too because, sorry, I can't select that. It's not literal too because the function says it returns an int. Yeah. Okay, what about this one? Is this valid? No, it's not. We get an invalid argument type because none is not an int. Okay, next we have a generic function. It takes in a t and it returns a t. Now we're passing in a 2. Is this valid? Yes. What's its type?
Literal 2.
Could be int, could be literal 2. That's a good one. Any others?
Object. Could be object.
Okay, that's good, but I want to do one more first. It could be int or none. It could be object. Okay. It could be supports index. This is a built-in protocol that says that it has a dunder index method. So protocols are interesting here because that's a structural type. Any type that implements the methods, would work here as well. So we could define any arbitrary protocol that talks about methods that int actually does have, and that's another type that this could resolve to if we wanted it to. So all of these are valid according to the type annotations that we have on the function there. Some of them are certainly less useful, are probably not what we would want to report to our users of the type checker, but there's nothing in the definition of the function that says that they're incorrect or invalid. Okay, what if we augment this so that we are not just calling this identity function, but we're also returning it, assigning the return value with a return type annotation? Here, in this case, we're actually constraining the valid solutions of t even more. And so here I would say that we've actually ruled out a lot of those sort of interesting pathological, maybe you would call them, examples that we came up with towards the end. And really at this point, we have just int and literal 2 as the possibilities for this one. Okay, so given that, I think, especially when you're talking about generic functions and type variables, I think it's less interesting to talk about if the expression is valid as a yes or no question, and instead we want to start talking about when the expression is valid. But what are the conditions that must hold on those type variables for the expression to type check correctly? So looking back at our first example, right, in order to call a function or any other callable, we need to make sure that the arguments that are provided match the parameters of the function. And so in this case, literal 2, the type of the argument, needs to be assignable to to int, the type of the parameter. Now in this case, there aren't any type variables, and 2 is a subtype of int, so this simplifies to always. This call is always valid. If we look at our none example, similarly, we're going to compare the argument to the parameter. None must be assignable to int, but it's not, right? So this is never valid. When we have our type variables, we do the same process. We say that 2, the literal 2, needs to be assignable to the type variable t, And at this point, we're just going to stop, right? This is an expression, a predicate, that tells us what needs to be true of our assignment to t for this to type check correctly. If literal 2 is assignable to t, then this is valid. And then for the example with the return type annotation, again, we do the same thing with our argument. We check that argument 2 is assignable to parameter t, but then we also have to look at the return type and make sure that the return type t, is assignable to that parameter annotation int. And so we have a more complex expression here. This wedge here is and, right? So this is saying that 2 must be assignable to t and t must be assignable to int. But you can think of this as an expression, again, that describes the entirety of the conditions that must apply for this expression to be valid. Okay, so to summarize, we've got the 4 examples. We can see that there are these expressions that express when each of those corresponding expressions, a Boolean expression that tells us when the Python expression is valid. Okay, now these are predicates, they're Boolean expressions. They, in some ways, take in an assignment and tell you, true or false, whether that assignment is correct. When you have a predicate like that, you can also think of it as a set, right? So in this case, the predicate literal true is a subtype of t. You can also think of that as a set of all of assignments where that predicate holds, where it's true. And you'll see we've got all of the examples here are the ones that that Vince McMahon helped us think through a few slides back, right? And the ... tells us that this in some ways is an open-ended set, right? Because we don't know in advance which protocols, which other structural types might be available to us. But the constraint set where we had that additional upper bound because of the return type annotation constrains us down further, and now we have a fixed size set with the 2 potential solutions there. Okay, so we can think of these either as a Boolean expression describing the constraints on the type vars, or as a set of assignments, what are the valid solutions. And so that is what led to the name constraint sets in TY. So this is a data structure that we're using internally to do this specialization inference. Okay, so now we can start to apply that same process to the running example, the motivating example from the very beginning. So we start off with choose, and we're calling it directly. We're not doing the partial application yet. But we're going to repeat the same process that we did a few slides ago. We're going to step through each of the arguments, and we're going to say that the argument has to be assignable to the corresponding parameter. So here, none must be a subtype of A. Next, the next argument, literal 2, has to also be a subtype of A. And that's it. We don't have anything constraining the return type, so this is the entirety of the constraint set that we get for this function. Okay, this is the Boolean predicate, right, the expression. We can also think of it in terms of a set of assignments, just like we saw a couple slides ago. So here there's 2 interesting solutions here. One is where A is mapped to none or literal 2. The other is where it's mapped to none or int. And we saw in multiplay that different type checkers were returning either of these assignments, but they both agreed that the none certainly need to be there, and the only open question was whether we were promoting the literal or not. Okay, so I'm going to take that constraint set there, and I'm going to move it up into the corner, because this is what we got as the correct result for the directly applied example. Now we're going to start looking at the partial application example, and this thing up in the corner is what we're aiming for. This is what we would like to try to reproduce, if we can. So now we've got the partial function that we carried over from the first slide, and we are assigning partial to p just like before, and then trying to call it with 2. So the first thing we need to do is figure out what the type of calling partial is. So what is the type of p here? And again, we're doing exactly the same process. The first argument is choose. It needs to be assignable to the type of the fn parameter. So we have the callable type on the left, which is the actual signature of choose. And the callable type on the right is what we've annotated the function parameter in partial with. So callable AA to A must be assignable to callable XY to Z. Now, 2 callables are assignable to each other, or one is assignable to the other, if the parameters line up and are respectively assignable to each other, and if the return type is assignable. Now, importantly, we do have to think about variance, so we had to flip the ordering for the parameters, but we don't flip the ordering for the return type. But we can simplify this expression to this. So passing choose as the argument for the fn parameter is valid, is correct, when x is assignable to a, and y is assignable to a, and a is assignable to z. Now we move on to the next argument. So next we need to add to the constraint set the fact that none must be assignable to x. Again, we don't have anything constraining the return type. So at this point we have what we might think is the full constraint set for this call. But we're actually going to start applying some high school math here because this doesn't give us all of the information we're going to need for the next couple of steps. So if you remember, you might know the transitive rule, which says that if A is less than B and B is less than C, then A is less than C. And so we have an example of that here in the constraint set. We have none is a subtype of X, and X is a subtype of A. And so that means that we also know that none has to be a subtype of A. And it's safe to add that to the constraint set here just because we have a bunch of things anded together. So that's a safe thing to add. We have another transitivity here that we can look at. None is a subtype of A, and A is a subtype of Z, so none is also a subtype of Z. So this is the same constraint set we had before. We've just iterated on a little bit to add some derived information that we can infer from the other facts that we know about. Why did we do this? Okay, so next, we're still aiming towards finding the type of P, which is the result of calling partial. So now we have a return type annotation here, which is what the result is, what the type of P is. And we have a constraint set that lets us solve for what we want Y and Z to be here. And we can see that none must be a subtype of Z, so we're going to choose none as the solution for that type variable. So we're going to say that Z is none. We can also see here that Y must be a subtype of A, so we're going to choose A as the solution for Y. So in each of these cases, we just found one of the constraints that talks about the type variable that we care about, and we're using its lower or upper bound as the solution that we want to choose there. Now, we can go one step further here, and we can see that none must be a subtype of A, so we're actually going to solve for A and then substitute that in as well. And the end result is that we solved this constraint set to get Y equals none and Z equals none. And then we substitute that in to the result, to the return type, and we get callable none, none. So this is what we have inferred as the type of P for this particular call site. And having done so, we can now see why we were getting errors, because we are trying to call a callable that takes in none and returns none, but we're giving it 2 as an argument, and 2 is not none, and so we get an invalid argument error. And if we go back to multiplay, we can see that is the error that we were getting, right? So argument of type 2 is not assignable to none. And if we go in, we can even add here another real type to verify that the type checkers are saying that each of them is inferring none to none as the type of that partially applied function. Okay, so this is explaining what went wrong. So the next step is to talk about what could we do differently if we wanted to support this instead. So taking a step back, remember we were at the point where we had callable Y to Z as the type for P, and we made the mistake, or maybe not mistake, but we were overzealous in solving for those type variables, and that's what led to problems. Now there was a step there where I said that we had mapped Y to A, and then we didn't want to keep that type variable A around, so we kept finding out what A was so that we could further substitute. But maybe we actually don't want to do that. Let's go ahead and accept that A might be our solution here, right? Because we see that A is a lower or upper bound of Y and Z, so this is a valid solution here. We can substitute that in and say that the result of partial is a function that takes in an A and returns an A. So in this case, partial P is still generic. And now if we were to call this with 2, this would succeed, right? We would say that this is an acceptable call, right? The solution we would get, though, is, I would say, even worse than the one that we had before. Because what we've done here is, the solution that we have here, if you'll notice, doesn't talk about none, right? It only says that A can be either literal 2 or int. So in some ways, we've forgotten the first parameter, right? So the first way that we went wrong is that we were thinking too much about the first parameter. We thought that none was the only thing you could pass in for either argument, and we were preventing you from doing anything else. In this case, we're actually going in the opposite direction, and we're under-constraining things. We're saying that you can pass in anything you want at all, and whatever you pass in is what we're going to give back. But we know that that's not the case. This choose function might randomly return none, and this return type is not taking that into account. So we've gone from having a false negative to having a false positive here. Okay, so let's do a third attempt here. What can we do again? So let's go back again. We have the result of partial being callable y to z. Now instead of solving for those type variables, which is what was causing the problem to begin with, let's just remember the entirety of the constraint set, right? We're going to simplify it so that it only talks about y and z. We don't need to worry about what it says about a, because that's in some ways like an internal variable that isn't visible to the caller. So this constraint set here on the bottom is the same as the one above, but with a quantified away. And completely inventing a syntax that doesn't exist, we could say that the result of calling partial is this, like you could think of it as a constrained callable. It's a callable that is not just generic on y and z, but there are these latent constraints on those type variables that we carry through in the type. And if we do that, then when we call p with 2, we're going to start that process again, where we start adding constraints for the arguments of this call site, but we're starting with those latent constraints that were carried along with the type. So we start with this restriction that y must be a subtype of z and none must be a subtype of z. And then we add the constraints for the arguments, here that says that literal 2 must be a subtype of y. And then we can do our transitivity like we were doing before. And that gives us a solution that remembers none from the first parameter, because that was carried along in the latent constraint, and also takes into account literal 2 or int that we're getting from the call site where we use that. And that is a solution that actually lines up with what we were getting when we were calling things directly. Okay, open questions. So I first want to call off that this example that I came up with very much relied on the fact that we were using partial application, because we needed to remember some things about some of the arguments until we used them later on at different places in the code, right? So I did a very basic search through the issue checkers of all of the different type checkers, the issue lists of all of the type checkers, and of the Python typing repo and of the Python discourse. And all of the cases where I could see people actually desiring behavior that looks anyway like this involves some form of partial application. So one open question is, just having described this mechanism, do any other folks think of other instances where this might be useful? That's particularly important because another open question is this even worth doing, right? If we decide that we maybe want to incorporate this idea of constrained callables, right? I've described a fairly deep mathematical notation, which is what those constraint sets would be. Is that adding too much complexity to the Python typing spec? And especially if there's only a small number of use cases where this would actually be useful, that's maybe not the right balance in terms of understandability versus expressiveness of the typing system.
Can it also be useful to express, sorry to interrupt.
Yeah.
For example, like a variable equals a literal, and then later on you assign a new value to the same variable?
So that is a very, very good question, and that is one that I think is a big can of worms that is worth discussing offline with a lot of people. So that's bringing in what we call bidirectional type checking, where the typing can be influenced by more than one expression collectively. And I think that this does give us a language that lets us talk about that. It's not necessary. There's other ways to do bidirectional type checking that I think Pyrefly and TY and Pywrite, several type checkers, already do. It's maybe something that would open up additional examples of bidirectional type checking working. So yes and no. An interesting question, yeah. Yeah, so if I understand the question, like there's maybe a way that this could be, right, like implementer's decision, like whether this is how we do it internally, but it doesn't necessarily have to be described directly in the typing spec, and that's absolutely a possibility too, yeah. I'll throw out the last open question because this really is the last slide here. Is the other bit is I haven't actually talked about implementation. I know Stephen's intro slide described this as the implementation of constraint sets, and I've talked about that absolutely none. So that's also an interesting area where we could maybe discuss offline is like how we actually do implement this currently in TY, because that's also very interesting. Yeah.
What do you mean by offline?
Not with me talking right now with these slides, but here in person over the next few days. Yeah.
Because I thought this room is as offline as it gets.
Yes, and I mean like yes. What I meant by that is I don't have slides describing how it's implemented. I would love to talk to it with people here today and for the rest of the weekend.
I believe we need a microphone, so the questions can be heard.
Yes.
Yes, we're actually recording this because we have a lot of people who couldn't make it here. Yeah, I'll run if you have questions. Anyway.
That's it. That's all I got. Yeah.
Could the code on the previous slide be fixed if you used two like different type variables, like A and B, and they made the return type a union of A and B?
You could. Yeah. That's. I mentioned that at the beginning that I did very carefully choose that I was using a single type variable. I think that if you did it where choose takes in A and B and returns A union B, I do think you still run into the same problems. What would you? Well, you know what? We can answer this question with data. Let's see. Because we have multiplay going. So at least we can answer it in terms of what everyone else does. And so here, yes, so Pyrite, for instance, is returning that partial remembers that B is generic and that the result does have the union with none. Firefly is doing the same. MyPy.
MyPy works except that random.choice has the wrong type.
Oh, yes, it does. That's true. Yes, thank you. Because we can't use random.choice here anymore. Well, should we?
Because it's joining instead of union.
Oh, it made it list of object instead of list of union. Yeah, very good.
I was saying,
Yeah.
I thought MyPy would have inferred a join on that first one. It would have 7 years
Yeah.
ago. At least.
But then Zuban does it right and then
But
refers.
apparently now
Yeah.
it'll join for the argument, or it'll union for the argument, but will still join for a list.
Yeah. Yeah, so yes, you're right. It would fix it that way. I think there's more complex examples where you can't necessarily do it that way, but in this case you can.
Hi. Yeah. So going into the implementation, I don't know how much you want to talk about it, but there are these subset-based inference systems, Portier's thesis, and I think Stephen Dolan or some other people with that.
Yeah.
So is it using those things?
We are using binary decision diagrams to implement the Boolean expression part. So the BDD variables are those individual constraints. We actually take that a little bit further and we've implemented, so there is type checking work in Elixir, which is using a lot of the same fundamental typing concepts, the set theoretic types that Python uses. And there is a PhD thesis that just got defended back in January, where one of the guys working on Elixir implemented an optimization to binary decision diagrams that adds a third outgoing edge for uncertain, in addition to true and false. So it's a ternary decision diagram, and that's actually what we've implemented.
Okay.
And then we have some horn clause database stuff on top of that to sort of do the derived facts that I was showing with transitivity.
Okay. Yeah.
And then from there, we have to do a path walk to get witnesses to get solutions. So that was the brief summary, but then I would be happy to dig into more when I can write and talk around the table.
And then follow up on the whether it's worth it or not. So one thing that I can imagine, even though you are like solving out A and like actually scoping the type variables, is there a chance that when you have too many constraints, then error reporting becomes really hard? And then because if you have a contradiction somewhere in the constraint set, then it's hard to point where.
Yes, that's exactly right. That's exactly right. That's one of the annoying questions that Carl often asks when I bounce these ideas off of him. He says, like, well, do our users actually care about it, and how will we report this to them? So when you get a contradiction, you do have to be able to, as you create the constraint set, you have to remember where each of the constraints come from, so that when you have a contradiction, you can trace through to show exactly where the contradiction came from. And in some cases, that gives you a direct mapping back to a snippet of source code. In some cases, it doesn't, yeah.
Okay.
What if the return type was itself generic? Like you declare a type variable on the return type and then set the upper bound as y,
So,
and then the return type is a union of that type variable in z?
so I think that is difficult because there isn't right now an easy syntax, at least not one that I'm aware of, for explicitly declaring that your return type is generic in that way.
Would that solve the issue?
So you would still need a way of expressing that additional constraint. And
Yeah, I said
if
to
the
make the
constraint is something that can be expressed as an upper bound on the type var, then yes. But the fact that it could end up being an arbitrary Boolean expression means that there are some that you can't express as an upper bound in that way.
Well, you have lower bounds too.
We have lower bounds too, yeah. And we have or and not. I didn't have any, like all of the examples that I show were just conjunctions, like a bunch of constraints anded together. But it's an arbitrary Boolean formula, so it could be or and not and arbitrary combinations thereof. So it's not generally true that any constraint set could be expressed as upper bounds on the type var.
So I'm curious, what's the current situation in TY with this? It's like you use constraint sets to solve things, but you don't yet generalize them into the types themselves?
Correct. And that first part is also in progress, right?
Okay.
So we are in the middle of migrating our generics solver to use constraint sets for all expressions. Right now, it's using it primarily for callables and other generics. But we have an older solver that is, I would say, an 80% solution that we're still in the process of migrating.
It is like a pretty big step to go from constraint sets as an implementation strategy to constraint sets as being like reified in the types.
Yes.
Because
well,
maybe I'm wrong about this, but like my model has been that currently it's hard to figure out the types in isolation, but like when you're done, you could still write down a type derivation saying like, okay, this could have had one of 12 different types, but here's the one it did have in a type derivation. I feel like you sort of, that blurs with this. And it might still be worth it, but it is like a big and interesting step.
yeah, and I think that there's already some heuristics where we do have, the type checkers do return callables that are generic,
Yeah.
right? And some of those are like heuristics to decide that that is what we want to return, right? So we already have in our implementation the fact that callable types that we create do optionally have
Yeah.
generic contexts. So from an implementation point of view, it's not actually that much of an extra step to say, well, we're also going to tack on a constraint
But
set.
I mean from
Yeah.
like a type system design specification point. So I guess I want to push back on the person who's saying, oh, this doesn't need a typing spec change. Because I think it is like a pretty big difference in the way that you think about it, or at least the way that I would think about it.
I don't know that
Which isn't like an objection, I'm just saying.
Yeah, no. I think it's a fair point. I guess I'm trying to articulate, I can see both sides of that because you could make the same argument about the fact that currently callables can be generic.
Sure.
Right. I think
But
that
like-
is mentioned that
but
it's
like,
possible, but it doesn't
take-
describe rules for when
but
we
like
do
taking a partially applied callable generic and then like regeneralizing the type variables, that's, yeah, no, that was like, that's pretty traditional in like polymorphic type languages, though it probably looks different.
Yeah, I mean, you can find both, right? There are some other languages that do explicitly lock it down to a single call, to a single solution.
Though, and
have
those like
partial
it's
application.
only when you're, yeah, we can talk about
Yeah.
some, yeah. All right, thank you, super interesting talk.
This is actually just a follow-up to this point. I mean, I think in a very practical sense, where the rubber meets the road on whether this needs to be in the typing spec is the fact that you have to show users error messages in which you have to describe this callable type somehow.
Yeah.
And so then you have the choice of either describing it, ignoring the constraint set, in which case you're sort of misleading them and that's confusing, or you have to come up with some syntax
Rendering.
with which to describe it, and users have to understand that somehow
Yeah.
and have some reference to go look for what it means.
Yeah, and back to, I think, I can't remember who it was, but somebody there had mentioned that there's the possibility of expressing these latent constraints as upper bounds on type vars. MyPy and Zuban actually do render some generic callables using a syntax which is not what you would actually type into Python to create the upper bound, but which is clearly isomorphic to that upper bound, right? So we could invent a syntax. Whether it would be understandable is an open question, or how we could make it understandable is an open question. I think there's at least prior art that we wouldn't necessarily have to force ourselves to align it with Python syntax.
There are systems like I was mentioning Stephen Dolan's thesis. He did this work in the context of camel, but it's kind of using like subtyping and so on, where there was actually a rendering of these constraints back into the types because he could prove that you could replace, depending on variance, upper bounds and lower bounds, and you would get a more general type using that.
Yeah, so
That was still a lot of restrictions needed to happen. You needed to have lattice operation.
yeah, and OCaml is a hard one because the type system that you're starting with is not set theoretic in the same way. It doesn't have union and intersection and negation types. Yeah.
Cool.
Okay, thank you, everyone.